This is Module 4, Enzyme Reactions, Kinetics, and Inhibitors. In this video, 4-4, I'll be describing the action of 4 different types of enzyme inhibitors, and also their effect on Vmax of an enzymatic reaction, and Km on an enzymatic reaction. In the last video, in 4-3, I described Km, the affinity of an enzyme for binding its substrate, as an intrinsic fundamental property of the enzyme, where Km does not change, it's a constant. It's a property of the enzyme. However, we can affect the affinity of an enzyme to bind its substrate if that enzyme is in the presence of an inhibitor. There are lots of natural inhibitors that happen in biochemical reactions. Many of them are actually the products of the reaction, so this is called feedback inhibition, where the product of the reaction will cycle back and inhibit the enzyme's ability to bind more substrate. So as product concentration increases, we don't really need more of it, and so the product itself will shut off the enzyme so it stops making product. By the way, if you can hear my daughter singing to the Frozen soundtrack in the background, I apologize. Anyway, so there are also types of drug-induced inhibitors, and so lots of drugs that have been designed to treat metabolic disorders or immune disorders. These are enzyme inhibitors. And so there are 2 types of enzyme inhibitors: irreversible inhibitors and reversible inhibitors. Irreversible inhibitors bind to the enzyme so tightly that activity is blocked forever. These are sometimes referred to as suicide substrates that enter the active site and then basically break the enzyme so that it's not able to unbind that inhibitor, and the enzyme is broken forever, can never bind another substrate ever. We're actually not going to talk about irreversible inhibitors. There's not too many of those in biological systems. However, there are 4 different classes of reversible inhibitors. Ones that bind the enzyme loosely so that enzyme activity is blocked, but only for a short period of time. These are reversible, non-covalent interactions between enzyme and inhibitor. There are 4 major types: competitive inhibitors, uncompetitive inhibitors, mixed inhibitors, and non-competitive inhibitors. I know what you're thinking. Uncompetitive and non-competitive sound like they're the same thing. I didn't name these things. I would have named them differently if I were in charge of that, but they are pretty different. Let's see how. Let's first start with competitive inhibition, which is a substance that directly competes with a substrate for binding to the active site. So here's our enzyme reaction, E plus S to ES, enzyme-substrate complex, and that yields enzyme and product. In the presence of an inhibitor, it will bind the enzyme before substrate has a chance to bind, and then form the enzyme inhibitor complex, and therefore no product is formed. So we're going this direction in the presence of inhibitor instead of in this direction. This also means that the inhibitor is competing directly for binding to the active site with the substrate. And so whoever gets there first wins, a direct competition. If substrate gets there first, great. It will form the ES and then eventually product. If inhibitor gets there first, that slows down the second half of this process, because inhibitor is going to have to come off and give substrate an opportunity to bind and then complete the reaction. This means one of 2 things: that high levels of substrate can overcome a competitive inhibitor. So if we put in 10 times more substrate than inhibitor, it's just more likely that this event will occur and this event will be less likely to occur. So this increases, this will actually help overcome this inhibitor. The other thing that this means is that these inhibitors that are competitive inhibitors look a lot like the substrate, and in fact, they look a lot like, so because they look a lot like the substrate, they can bind so tightly within that same active site and then prevent something like a transitional molecule from forming. So this inhibitor will stabilize the enzyme inhibitor complex, and then it will be difficult for it to bind substrate. There's something blocking its way. And so these inhibitors are very similar in structure to the substrates they're competing with. They're both binding to the same place with geometric and electronegative complementarity. An example of a competitive inhibitor in our body in a biological competitive inhibitor is the competitive inhibitor for succinate dehydrogenase. This reaction is part of a metabolic pathway called the citric acid cycle. Succinate is the substrate, fumarate is the product, and the enzyme that catalyzes this reaction is succinate dehydrogenase. Later on in the citric acid cycle, this product, malonate, is made. Malonate, if it gets in too high a concentration, will try to slow down the entire pathway by binding directly to the active site of succinate dehydrogenase, and no reaction occurs when this happens. So fumarate cannot be made because malonate is in this enzyme blocking the ability of succinate to bind in the first place. How does this affect our Michaelis-Menten plot? During competitive inhibition, a substance again is directly competing with a substrate for binding to the active site. And so what happens is it looks as though the apparent affinity of the enzyme for its substrate, or the Km, increases. If the Km is increasing, that means the affinity for the enzyme binding its substrate is decreasing. Remember, this thing is competing directly in the active site. And we just said on this other slide that high levels of substrate can actually overcome this process because this event is more likely to occur than this one. And so if we can increase the substrate concentration, as we increase it, eventually we will reach the same level of Vmax. Eventually there'll be so much substrate in this solution that substrate is most likely to bind enzyme and the inhibitor has no action. So eventually we will get to Vmax. The substrate can still enter the active site when it's in high enough concentration, when inhibitor isn't bound. And so eventually product is still made. And so we'll still get to the end point, the saturation point, as long as you saturate the reaction with substrate. Km, however, will increase. It's going to take more substrate to get to half Vmax. That makes sense because there's an inhibitor in there blocking its way. And so we got to increase the amount of substrate. So that's going to increase the Km, and that looks, so increasing the Km would mean enzyme affinity for substrate is lower in the presence of an inhibitor. Let's look at the next class of inhibitors, uncompetitive inhibition. This is a process in which a substance binds to the enzyme after the substrate has already bound. This means this inhibitor looks totally different from the substrate because it's binding in a different place, at a site that's very near the substrate. And so what happens here is enzyme binds substrate first, and then an inhibitor will bind to the enzyme and tighten the interaction between, it will stabilize the interaction between the substrate and the enzyme, and therefore the transitional phase, the transition state, can never be reached. The enzyme binds its substrate so perfectly and so tightly that it's not able to create the transitional molecule required to make a product. And so, what effect will that have on affinity and Vmax? During uncompetitive inhibition, again, the substrate binds to the enzyme once the substrate has already bound, and then increases the stability between the enzyme and the substrate, making it impossible to create a transitional molecule. What that does to Km is it makes it look as though the enzyme is really good at binding its substrate. It tightens the interaction between enzyme and substrate. And so Km will appear to decrease. The binding of the inhibitor will cause more enzyme to bind to substrate, and less enzyme is able to get recycled, right? You can't go from enzyme substrate to product, and then that enzyme is not able to bind another substrate. So it looks as though enzyme binds its substrate so tightly that it can't actually make a product. And so affinity increases, Km decreases. What's interesting about this is that because enzyme binds its substrate so tightly and cannot then make a product, this means we can't recycle the enzyme. We can't get the enzyme back. And so when ES binds to an inhibitor, that essentially removes all of those enzymes from the reaction. Those enzymes are no longer able to function. And so it looks as though we decrease enzyme concentration, because some of those enzymes are now broken and we can't get them back. They're not able to make product. And so it looks as though Vmax will decrease. Just like how when you decrease enzyme concentration, Vmax comes down, in the presence of an uncompetitive inhibitor that prevents ES from making product, makes it look as though enzyme concentration has decreased. Okay, now let's talk about mixed inhibition. A mixed inhibitor is one that can bind to the enzyme directly, and then it binds its substrate, or it can bind to the enzyme-substrate complex. So again, this inhibitor is binding someplace else other than the active site of the enzyme. So this is the active site of this enzyme. If inhibitor binds to the enzyme first, it changes the shape. It will allow, so if enzyme binds the inhibitor first, substrate will then bind and then product can't be made. If substrate binds first and then inhibitor, then product cannot be made. And so the effects of a mixed inhibitor on Vmax and Km are a little bit hard to predict. Usually, any one inhibitor has different affinities for either binding the enzyme alone or binding the enzyme-substrate complex. So what does that mean? Well, let's say we have one enzyme that's capable of binding two different types of inhibitors. One of those inhibitors really likes to bind the enzyme alone before it binds substrate. The other inhibitor likes to bind the enzyme once it's already bound substrate. Both of those would be considered mixed inhibitors. But because there's an affinity of binding one over the other, this makes Km really difficult to predict. So let's look at what happens to enzyme kinetics in the presence of a mixed inhibitor. So again, this occurs when an inhibitor binds to an enzyme and alters the conformation of the active site so much that Vmax decreases and Km can do either. Okay, so for the reason that Vmax decreases here, this is the same rationale behind why Vmax decreases in the presence of an uncompetitive inhibitor. In order to prevent product from being formed, all three have to come together. It's just what order does this occur in varies. It's because the mixed inhibitor can bind directly to the enzyme or to the enzyme-substrate complex. But in both cases, it's binding an alternative site, and it's going to increase the stability between the enzyme and the substrate, which will forbid a product from being made. And so for the reason that Vmax decreases in the presence of a mixed inhibitor, it's the same reason why it decreases for an uncompetitive inhibitor. It looks as though we're taking enzymes out of this solution because the enzymes that are bound to substrate an inhibitor can't make a product. They're so stable in that form that product can't be made and substrate will rarely fall off. Okay, so let's talk about Km. It's much harder to predict here. If the inhibitor has a greater affinity for the enzyme alone, Km will appear to decrease. This is because this is related to competitive inhibition. So like I was saying, for a mixed inhibitor, if the affinity of the inhibitor for binding enzyme alone is best, then Km will appear to decrease. If the enzyme inhibitor has greatest affinity for binding the ES complex, Km will appear to increase. So it's really hard to predict what's going to happen here with Km. It really depends on where the inhibitor is binding first, either the enzyme alone or the enzyme substrate complex alone. It really depends. So we don't really try to predict what Km is going to do for a mixed inhibitor. It's really hard, but we do know that Vmax will decrease in both cases. Let's look at a non-competitive inhibitor, which is sort of a form of mixed inhibition. But in this case, the affinity of the inhibitor to bind the enzyme or the enzyme-substrate complex is exactly the same. And so if the inhibitor can bind the enzyme and the enzyme-substrate complex with the same affinity, then there's still this decrease in Vmax. Vmax will decrease for the same reason that it decreases in an uncompetitive inhibitor. It looks as though we're taking enzyme out of the solution because enzyme cannot make product. But Km will stay the same. There'll be no change in Km. Think of it this way. If this inhibitor is acting like a competitive inhibitor, where it's binding directly to the active site. So here we have an enzyme, we have an inhibitor, and the substrate. The inhibitor and the substrate can bind independently of each other. So sometimes inhibitor binds first, and sometimes substrate binds first. If inhibitor binds first, completing the reaction depends on the enzyme undergoing a conformational change, which can't happen. It's blocked by the inhibitor. And so a product is not formed. If the substrate binds first, then the inhibitor has to bind, and then again, no product is formed. And the inhibitor is binding to a different site. So it doesn't stop the ES from forming. Okay. So the Km ends up being about the same if the inhibitor is binding both the enzyme or the enzyme substrate complex with equal affinity. Okay, let's move to allosteric enzymes. So we're moving away from the inhibitors. Let's talk about allosteric enzymes. Allosteric enzymes are multi-subunit enzymes where action at one subunit affects the ability for the neighboring subunit to do its job. So you can sort of think of hemoglobin as a type of allosteric molecule, but we don't call it an enzyme. Hemoglobin's not an enzyme. Allosteric enzymes are responsible for regulating the flow of metabolites through metabolic pathways. And so we tend to find allosteric enzymes often in metabolic pathways. And we're going to explore a lot of those when we talk about glycolysis and the citric acid cycle. The activity of an allosteric enzyme is regulated by effector molecules. These are small molecules that bind the enzyme at a different subunit than the active site. But when that binds, it changes the shape of the active site. Activators, when they bind to an allosteric enzyme, will make the active site more available to substrate and increase the reaction faster. Inhibitors, when they bind an allosteric enzyme, will change the active site so that it's not as good a complement for its substrate, and its substrate won't bind as well. There are two different types of allosteric enzymes. Homotrophic enzymes, where one molecule acts as both the substrate and the allosteric effector, and heterotrophic enzymes, one in which the effector molecule is different from the substrate, and they bind in different places. Let's talk more about heterotrophic enzymes because those are the ones that are more involved in biochemical reactions. Okay, so here's our allosteric enzyme. And this is a type of cooperative binding. Our substrate is pictured here, and so this is the active site. And then this is the modulator. This is binding to the regulatory site. And we have two different subunits, right? So here's the active site, here's a regulator site. If we have a modulator that is positive, meaning it encourages binding at the active site, the modulator binds here, and it will change the shape of the active site to fit the substrate a little bit more tightly. And then that will increase the enzyme's ability to bind substrate, and then eventually its overall catalytic efficiency. So if something binding to one subunit affects the rate of binding at the other subunit, what shape is that going to look like on a reaction coordinate? It's going to look a lot like hemoglobin, this sigmoidal curve. And because allosteric enzymes have this sigmoidal curve, where the initial velocity is much faster than a little bit later in the reaction, or the other way around, depending on what type of inhibitor is present, a positive or a negative one, we can't really use the Michaelis-Menten equation in order to predict kinetics of an allosteric enzyme. Here's an example of what I'm talking about when I say allosteric enzyme. This is a metabolic reaction involved in the metabolism of amino acids, so breaking down amino acids to use for energy. The two substrates for this enzyme, ATCase, are carbamoyl phosphate and aspartate. These are two substrates that have to join into this enzyme to create this product, N-carbamoyl aspartate. This is then further processed in 6 other steps, and one of those steps yields this product, CTP. CTP is an allosteric inhibitor of this enzyme. And so if this enzyme is working very quickly, making a lot of product, then a lot of CTP is going to build up. This is going to build up in high enough concentration that it will contact this enzyme, bind to it, and slow down the rate of this reaction. And so this is an inhibitor of this enzyme. We can see that on this chart here. So note the sigmoidal curve where the rate is very quick initially and then slows down. And the rate is very slow at first and then increases because there's multiple subunits here. In the presence of an inhibitor, the curve shifts to the right. And what that means is it's going to take a lot more substrate, aspartate, to get to the end of this reaction in the presence of the inhibitor. It's not making product as quickly. And so we're going to have to really ramp up the amount of substrate in there to encourage the enzyme to bind aspartate over the CTP molecule.